Okay, so good morning. Okay, so today we are going to look at uh, the game of minimum distance. I will show you how minimum distance is useful in detecting errors and correcting errors. Before that, I'll give you a couple of examples, and then I will tell you about the main results. Uh, okay, so we the topic is game of minimum distance. I'm talking about having distance. Game of minimum distance. Okay. So we were looking at a code. So I am assuming that our code is simply a subset of z2 raised to power and a binary code I am taking. So C is specified by the parameters n, capital M, and D. Okay. So the total number of code words in C is capital M. N is length of the code, and D is minimum Hamming distance. I think I described you the Hamming distance last in the last lecture. So this is also denoted by D of C. Okay. Especially for binary codes, we also have one special relationship. If WH of X denotes weight, which means number of non-zero positions. Okay. So that means if X is a vector, something like x1, x2, xn. So I can just look at what are the positions which are non-zero. So then we can compute the weight. For example, if x is 11010, the weight of x is 1, 2, 3, 4, 5. Okay. So with this weight in hand, we can actually say that Hamming distance between two vectors x comma y is nothing but Hamming weight of x minus y. Okay. So weight of x minus y. Or in fact, in case of binary, this is weight of x plus y. So this is true for linear codes actually, when code is linear. But anyway, this is a very basic thing. Means it's a subspace. So now let me give you some examples. Suppose C is a code with code words this. So I need to find out the parameters of this code. So this is your one code word. This is another code word. This is another code word, third code word. So I can say that distance between x comma y is 3. Number of places they differ is 3, right? Similarly, distance between x comma z is 5. The number of places x and z differ in 5 places. and distance between y comma z. C is a 532 code. Is here 2 median distance, because we can compute the pairwise distance between all code words, and it turns out that 2 is, so C is a 532 code. If we take another example, so in this case, suppose C is 1, 2, 3, 4, 5, 6, then 0, 0, 0, 1, 1, 1, then 1, 1, 1, 2, 2, 2. This is an example of code actually. It is a subset of Z3 raised to the power 6. Okay, it's an example of ternary code. So I can denote its parameters by C is 6, 3, 3, 4. Okay, I can compute what is n. N is 6, length is 6. Total number of 3. There are only 3 code words. And minimum having distance I can compute. It turns out to be 3. Okay. Now we define what is known as error detecting code. Okay, error detecting code. A code C is called error detecting. Okay, so basically we call error detecting. Of course, S is a positive number here, integer. Whenever a code word occurs at least one, but less than or equal to S errors, and the resulting code word is not a. So basically, I should say resulting word actually, resulting vector. Word is not a code word. So we started with a vector x. Okay, that means if we start with a vector x in C, right, and S error occurs, and if y is, suppose y is the resultant vector and y does not belong to C, then we say that it's S error detecting, right? So this is S error detecting. Let us take an example. Let C be a binary code I am taking 0 0 1 1 1 1 1 1 1 1. So you can see that it is a one error detecting code. Why it is one error detecting? Because if you take any code word and change it in position, right? So suppose I take 000, 00000, I change it in the last position. I change it in one position and vector is 0001. This does not belong to C. I can take any one, I can take say 11111 and change it in the last in say second last position 11101. This does not belong to C. I can take any code word and it change in one position. This does not belong. This is resultant vector is not a uh, another code word, right? So this is one error detecting. Okay, S is one here. Okay, so one error detecting. So now I can take another example. So now suppose C is your 6 zeros, 000111 and then 111222, right? So this is a two error detecting code. Why? Because if you change any code, take any code word and change in one or two positions, does not result in another code word. Okay, so this is known as two error detecting code here because this is I have taken an example of ternary code. Okay, now I think I am going to give you a result here. This is a theorem, and is that C is S error detecting C is S error detecting if and only if minimum distance of C is at least S plus 1. This is a very beautiful result. So the minimum distance is so if C is NMD code, right? So we know that. So we can try to prove it. C is our NMD code, right? So D is it's so that means if you take any two code words X and Y in C, the distance between X comma Y will be at least D, right? This is at least D. If you take any two code words X and Y in C, the distance between X and Y is at least D. That is because D is the minimum distance, right? Now, suppose so we want to first prove this way. This way. So we assume that this is true and we'll try to prove that C is S error detecting. Suppose minimum distance of C is at least S plus 1, okay, and X is a code word and Y is a resultant vector. Y is a vector such that distance between X comma Y is less than or equal to S. So S errors have occurred, right? X is a code word, y is a receipt vector, and s errors occur. So that means the distance between x comma y, up to s errors occur between 1 and s, right? Now this s is strictly less than d. Why? Because d is at least s plus 1, minimum distance is at least s plus 1. So s is less than or equal to d minus 1, which is strictly less than d. So this is showing us, so that means distance between two code words x comma, so distance between x comma y is less than d. So basically y cannot belongs to c, right? This implies that y cannot belongs to c, since distance between x comma y is less than d, right? Whereas we know that distance between any two code words has to be at least d. That means y, right? And hence c is s error detecting, right? On the other hand, so now if you want to prove in this direction, I will assume that, suppose distance of c, so we have to assume that distance of c is at least s plus 1, right? Suppose it is not, then we'll show that it is not s error detecting. We'll show that suppose d of c is less than s plus 1. This implies that minimum distance will be less than or equal to s. Okay. Now this implies that there exist two code words c1 and c2 in c, such that distance between c1 and c2 should be at least 1, or should be, this distance is d, right, of c, which is less than or equal to s. This implies that we started with 1, and and there are, and dc errors are there, right? dc errors occurred, and c2 is another code word, right? c2 is another code word. Okay. Hence, since if c2 is outside c, then it is s error detecting. Here basically, since c2 is another code word, so c is not s error detecting. Okay, so this is a nice result. So I'll just summarize. The result says that c is an s error detecting code if and only if minimum distance of c is at least s plus 1. This is a very fundamental and basic. Okay, now I think I can talk about error correcting condition, and that's also very, very error correcting condition is a code. This is theorem. A code C can correct up to T errors in any code word if minimum distance of C is at least 2T plus 1. Very beautiful result. And you see, so the condition on DC minimum distance of C can tell us how much errors it can detect. It can also tell us how many errors it can correct. And so this is the result. So a code can correct up to T errors in any code word if minimum distance of C is at least 2T plus 1. Okay, so let me show you this result. Very beautiful result. Let us start the proof. Okay, suppose minimum distance of C is at least 2T plus 1. Okay, we know that minimum distance is at least D, right? Of between any two code words. Suppose it is 2T plus 1. C is our NMD code, of course. We assume that C is our NMD code. Okay. Now, suppose X vector is sent, and Y is received. This is sent, and Y is received. Okay. And suppose T of fewer errors occur. Okay, T of fewer errors occurred. In that case, what will happen? The distance between X comma Y cannot exceed T because T positions will flip, right? Okay. Now, so I think I should draw a small picture here. These are all code words in C, right? And we know that the minimum distance is at least 2T plus 1. That is given here. Minimum distance is at least 2T plus 1. Okay. Suppose X is this code word here. Okay. Now my claim is, how do I correct errors? Remember, in order to correct the errors, so if suppose X is sent, Y is received, then we compare Y with every code word in C, and whichever has the least, whichever is close with respect to distance. So the distance of Y with X is least among all code words. So that is then we say that suppose a distance of Y with X is least, then we say that X is the actual code word that was sent. This is how we correct the errors, right? So that we need to keep that thing in mind. X is sent, Y is received, T of fewer errors occurred. I want to show that X is the actual code word which was sent. Suppose there is another code word X prime, which is not equal to X. Suppose there is a code word X prime in C. Okay. So of course X prime is not equal to C. So the claim is the distance between X prime and Y, received vector Y, will be at least T plus 1. Okay. So this is more than, because the distance between X comma Y is T, right? X is sent, Y is received, and distance between X comma Y is T, at most T. Now if we pick up any other code word X prime, so distance between received vector Y and any other code word is more than T, right? It is at least T plus 1. If we are able to show this, that means the least weight vector, the least distance is between Y and X, and so X is the actual vector which was sent, right? So X is the decoding. So by nearest distance decoding, we'll be able to decode the code word. Okay, so we need to now show that only this portion. If X prime is any other code word, then d of X prime comma Y is at least T plus 1. It is more than T. Suppose, or otherwise, suppose it is not. Suppose this distance is X prime comma Y, distance is less than or equal to T. Suppose it is opposite side, right? This implies that I can compute the distance between X and X prime and see what happens. We know that this distance between x and x prime, because x and x prime both are code words. So these two distance between x and x prime should be at least d, right? Because d is the minimum. If I pick up any two code words, the minimum distance between any two code words is in this case. So distance between x comma x prime cannot exceed, by triangular inequality, distance between x comma y plus distance between x prime comma y. Now distance between x comma y is less than or equal to t from here, from this condition, and from this condition, we have t. So overall thing is 2t, right? That means distance between x comma x prime cannot exceed 2t, which is a contradiction. It is a contradiction to the fact that distance between any two code word is at least 2t plus 1, and this distance turns out to be less than 2t. So this is a contradiction, and hence we are able to correct. So that means distance between any other code word x prime with the seed vector y is at least t plus 1. So since distance between the seed vector y with any other code word other than x is more than t, so we can say that x is the actual code word that was sent, and so this is how we decode the code word. Okay, so I think these two results can be summarized in another way, writing that for you. So okay, so result I can summarize in a compact form. If C has minimum distance d, then C can be used to correct greatest integer d minus 1 by 2 errors and d minus 1 errors. And the answer is really simple. Why? Because in case of S error detecting, we know that if the distance is at least s plus 1, the code is S error detecting, right? And this condition gives us that S should be less than or equal to d minus 1. So we can correct up to d minus 1 errors. Second result, when the minimum distance is at least 2t plus 1, and this condition is true if and only if t is less than or equal to d minus 1 by 2, right? So we can put this ceiling. So this result holds. It can correct up to d minus 1 by 2 errors. T is number of errors it can correct, right? So this is a really very basic result. So that means if C is a NMD code and D is the minimum distance, then C can be used to correct D minus 1 by 2 errors, right? And it can detect up to D minus 1 errors, right? So this is a very, very basic result and very important result to memorize. And I think we will need it quite often. Okay, so now I will show you something really interesting. Uh, I will show you how to form a sphere. Okay, so in this space, so we know that G to n is all code words of the form x1, x2, all vectors of the form x1, x2, xn, such that xi belongs to Z2. Okay, this is our binary vector space. This is our binary vector space. binary vector space. Now, suppose C is a NMD code, simply a subset of Z2 raised to power n. Okay, NMD code, binary linear code, and we know that it can correct up to T errors. So T is D minus 1 by 2. Okay, T errors can be corrected. Now, I can draw a sphere of radius r around a vector u. I can define it as all those vectors v or u. Yeah, it is around a vector u. U is a vector in C. All those vectors v in z2 raised to power n such that distance between u comma v cannot exceed r. This is the definition of sphere. Okay, let me take an example and see what are these spheres are. Suppose okay, suppose C is our vector 0 0 0, code is 1 1 1, right? This is a subset of z2 raised to power 3. It's a binary. Of course, it is a linear code, but we are treating it as a non-linear code right now. Okay, simply a subset. Now, if you recall the definition of sphere, right? Is all those vectors y in z2 raised to power n such that distance between x comma y cannot exceed r. So x is a code word in C, right? So let us take and draw is so basically this code C is, what are the parameters for this code? Length is 3, total number of code words 2, and minimum distance is 3. So D is 3 here. If D is 3 here, so T is what? T is greater than 0, D1 minus 1 by 2, which is 3 minus 1, which is 2. So this is 1. It's a singular error correcting code, right? T is equal to 1 here. So let me draw a sphere of radius 1 around a code word 0 0 0, and I would like to see what is the value. So by definition, it is all those code words y in z2 raised to power n, z2 raised to power 3 here, such that distance between x comma y, so such that distance between 0 0 0 and y should not exceed 1. Okay, so we know actually I can write down what is the value of z23 here so that we know all the code words. 0 0 0, okay, 1 0 0, 0 1 0, then 0 0 1, 1 1 0, 1 0 1, 0 1 1, and 1 1 1. These are all 8 code words in the whole space. I take the vector from all of them, right? So our S100 will consist of 0 0 0. That will be part of it, right? Because the distance should not exceed 1. Then 100 and distance between 100 and 000 is 1, right? So this will be a part of it. Then distance between 010 will be a part, and distance 001 will be a part of it. If I take 110, so distance between 110 and 000 will be 2. So this cannot be there. These are more than 2, right? so we are left with this. Okay. Now if I take the other sphere of radius 1 along other code word 111, if we take the sphere by definition, so I have to look at all those code words in the space Z23 such that the distance between all those code words with 111 cannot exceed 1. So you see what are the code words that will come. So we will have 110. So basically what we will have here, of course we will have 111 vector here, then we will have 110, 101 and 011, right? So you can see that the distance between 111 and 111 is 0, of course, so we have to include that. Then distance between 111 and 110 will be less than 1, less than 1, less than 1 for all other code words. So these are the two spheres. Now what you observed here, it's a very beautiful thing, that these two vectors actually S1 0 0 0 and intersection with S1 111 is empty. Okay, these two sets are disjoint, these two spheres are disjoint, there is nothing common between the two. Okay, so can we prove this thing in general? Answer is yes. Not only this, in this particular case, in this particular example, it turns out that uh, you know mm, uh, they cover the whole space, right? So they are disjoint, and also if you take the union, you get the whole set z2 raised to power 3, right? So let's first check. So we want to establish the following result. If C is NMD code and T is I want to show that ST of X ST of C1 or ST of C intersection ST of C prime is phi, where C and C prime are two code words of C. Okay, so that means if you are taking capital C as NMD code, which is T error correcting, I draw the spheres of radius T around two code words C and C prime. They will be disjoint. That's what we have shown you here in this example. Now I am going to prove it. In order to prove it, suppose they are not disjoint and X is a vector which is common to both. Suppose X belongs to ST of C intersection ST of C prime. Okay, X is common to both. Then you know by definition, since X belongs to ST of C, so distance between X comma C by definition of the sphere cannot exceed T, because T is the radius of the sphere. Similarly, we have the distance between X and C prime cannot exceed T, right? Both the distance cannot exceed T. Now if I compute distance between C and C prime by triangular inequality, I can say that this is distance between C and X plus distance between C prime and X. Okay, and now this distance here, we just know that this distance is less than or equal to T plus this distance is less than or equal to T. So overall distance cannot exceed 2T. Okay, now we know that since these d minus 1 by 2, so the distance is at least 2T plus 1, right? This condition we know. Now, so that means the minimum distance of any two code words has to be at least 2t plus 1. But here what we are getting, the distance between C and C prime, both are code words, cannot exceed 2t. So this is a contradiction, right? So contradiction. And hence our assumption that these two are not disjoint is not correct. And hence ST of C intersection ST of C prime is phi. They are disjoint. We just, okay, so they are disjoint. Now actually this sphere thing is quite useful in telling us how to correct it. So let me show you one picture here. Okay, so x is a vector. Okay, so basically I am just, okay, here is our whole space. Okay, and suppose this is our C, right? X is a vector here. Suppose x is sent. Okay, this is another vector x prime. X is sent, y is received. X is sent, y is received, and t errors occur. Suppose distance between x comma y cannot exceed t, right? So and of course the code C is an MD code. Minimum distance is at least 2t plus 1, or in other words, t is greater than 0, d minus 1 by 2. So if x is sent, y is received, you know. So basically we say that y is received here. Suppose if y is outside C, then we know that we cannot correct it, right? It has to be inside C. So basically now you see that and sphere, so these spheres are disjoint. X is sent, y is received, t errors occurs. As soon as t errors occurs, the distance between x comma y cannot exceed t. So this will fall in right? Distance between x comma y cannot exceed t, right? So it will fall in this sphere. That means we know that x is the original code word which was sent. So you sent some code word x, draw the spheres of radius t along each code word, right? And suppose t errors occur, right? X is sent, y is received, t errors occurred. Then x cannot go beyond this sphere. It will fall into one of these sphere, right? So we will be able to correct the errors. So this is how we call it sphere decoding, you know. This is a this decoding technique is known as sphere decoding. So what we do in order to decode, take a code word C. For each code word in C, draw the spheres of radius t, where t is greater than integer d minus 1 by 2. Right, these spheres are disjoint. X is sent from any sphere, the center you can send. X is sent, y is received. If t errors occurred, y will fall into one of the sphere, right? Because distance between x and y cannot exceed, right? If t errors occurred, so it will fall in the sphere which has x as its center, right? So now we say that okay, center is the actual code word that was sent. This is how we correct the errors. Okay, this is known as sphere decoding. So now any question at this point? I think I would like to ask you any question at this point.